Imagine walking up to a fence that stretches farther than your eyes can see. It stands through storms, blazing heat, freezing winters, and sometimes even impact from vehicles weighing thousands of pounds. Yet most people never stop to ask a simple question. Where did this wall of steel, wood, or wire actually come from? What you're about to discover is a hidden manufacturing journey that begins deep beneath the earth and travels across continents before a single fence panel ever reaches your backyard. Think about this. Every year, manufacturers produce enough fencing to circle the earth multiple times. Some fences protect homes. Others surround airports, military bases, factories, power stations, and massive industrial sites worth billions of dollars. But here's what nobody tells you. Creating something as ordinary as a fence requires mining operations, giant steel mills, precision engineering, robotics, and quality systems that rival those used in the automotive industry. And this is where it gets truly extraordinary. Before the first fence post rises from the ground, raw materials may travel more than 10,000 miles through mines, forests, rail networks, cargo ships, and factories. Along the way, temperatures soar hotter than volcanic lava. Machines apply forces strong enough to crush automobiles, and engineers measure dimensions thinner than a human hair. The journey starts far from neighborhoods and gardens. It starts where nature hides the ingredients. For steel fencing, everything begins with iron ore. Some of the world's largest supplies come from Australia's Pilbara region, Brazil's Carajás mine, and parts of India and South Africa. These mines extract ore that often contains between 55 and 67% iron. Massive haul trucks carry more than 300 tons rumble across dusty landscapes day and night, creating a constant roar that echoes across the open pit. Most people never think about it, but a simple fence may trace its origins back to rock blasted from the earth thousands of miles away. The mining process starts with drilling and controlled explosions. Engineers calculate blast patterns with remarkable precision, breaking millions of tons of rock into manageable fragments. Giant excavators scoop the ore into trucks taller than a two-story house. The ground shakes, engines thunder, and clouds of dust rise into the air. What happens next surprised even experienced engineers when modern automation transformed entire mining fleets. But steel isn't the only path. Millions of wooden fences begin in managed forests across Canada, the United States, Scandinavia, and parts of Eastern Europe. Species like cedar and pine dominate because they resist insects and moisture better than many alternatives. Some cedar trees grow for decades before harvest, storing carbon and developing the strength needed for outdoor use. Imagine a tree standing quietly through countless winters before eventually becoming part of a backyard fence. For chain-link fencing, another critical ingredient enters the story: zinc. Large zinc deposits in countries such as China, Peru, Australia, and Mexico feed galvanizing plants around the world. Zinc protects steel from rust by forming a sacrificial barrier. Without it, many fences will begin deteriorating within years. With it, some can survive for decades while facing rain, snow, humidity, and salty coastal air. After extraction, raw materials begin an astonishing journey. Iron ore travels by rail to ports, then onto cargo ships carrying hundreds of thousands of tons at a time. A shipment may cross entire oceans before reaching a steel mill. The scale feels almost impossible to comprehend. One vessel can transport enough or produce steel for miles of fencing, highways, buildings, and bridges all at once. At steel plants, ore meets coal and limestone. Coal eventually becomes coke, a fuel rich in carbon that drives steelmaking. Limestone removes unwanted impurities during refining. Together, these materials create a carefully balanced recipe. Even tiny changes in chemistry can affect strength, flexibility, corrosion resistance, and the lifespan of the final fence. Environmental challenges follow every step. Mining alters landscapes. Transportation consumes fuel. Steel production generates significant carbon emissions. That's why many manufacturers now recycle enormous amounts of scrap steel. In some facilities, recycled material accounts for more than half of the metal entering production. A fence you see today may contain steel that once formed part of a demolished building, an old vehicle, or industrial machinery. Meanwhile, harvested timber heads toward sawmills. Long logs arrive on specialized trucks and move on to conveyor systems that scan each piece using lasers. Computers calculate the most efficient cutting patterns, maximizing usable wood while minimizing waste. The scent of fresh timber fills the air as blades slice through trunks with astonishing speed and accuracy. Whether the fence will be steel, wood, aluminum, or chain link, every raw material now converges on a common destination: the manufacturing plant. This is where rough ore becomes precision wire, where timber transforms into finished panels, and where ordinary materials begin their evolution into products trusted to stand guard for decades. But what happens inside those factories involves heat, pressure, speed, and engineering on a scale few people ever witness. And the moment those materials enter production, temperatures will climb above 1,500 degrees Celsius. Molten metal will glow brighter than the sunset, and machines will shape thousands of feet of fencing every hour. What happens next is the heart of the entire story, and it's where fence manufacturing becomes truly spectacular. The moment raw materials arrive at the factory, the real transformation begins. Forged steel fencing, giant coils weighing up to 25 tons roll into production lines that stretch hundreds of feet across the plant floor. Motors hum, conveyors rumble, and warning lights flash as automated systems prepare for non-stop production. Imagine standing beside a machine that can process enough steel in a single shift to build miles of fencing. The sound alone feels like an approaching freight train. Everything starts in the steel mill, inside a blast furnace operating at approximately 1,500 degrees Celsius to 2,000 degrees Celsius, or 2,732 degrees Fahrenheit to 3,632 degrees Fahrenheit. Iron ore combines with coke and limestone. Powerful air systems inject heated oxygen-rich air into the furnace, triggering chemical reactions that separate iron from impurities. Molten iron glows bright orange-white as it collects at the base. The heat feels almost impossible to describe. Even standing dozens of feet away, workers can feel waves of energy pressing against their protective suits. Next, the molten iron enters a basic oxygen furnace or electric arc furnace. In an electric arc furnace, recycled steel often joins the mix, and powerful electrical arcs hotter than the surface of the sun melt the metal. Temperatures remain around 1,650 degrees Celsius, or 3,002 degrees Fahrenheit. Sensors constantly monitor carbon levels, alloy content, and impurities. Engineers adjust chemistry in real time, because even a tiny variation could weaken the finished fence years later. The refined steel then moves into continuous casting machines. Here, molten metal flows into water-cooled molds and begins solidifying almost instantly. Giant slabs emerge at speeds reaching 1 to 6 meters per minute. Steam erupts as cooling systems remove enormous amounts of heat. What moments earlier looked like liquid fire now become solid steel ready for shaping. Those slabs travel to rolling mills where powerful rollers exert thousands of tons of force. The steel passes through multiple stages while temperatures remain near 1,100 degrees Celsius, or 2,012 degrees Fahrenheit. Each pass makes a material thinner, longer, and more precise. Sparks dance across the floor. The smell of hot metal fills the building, and every second, the steel changes shape under incredible pressure. For chain link fencing, the steel enters wire drawing machines. Thick rods feed through a sequence of hardened dies, each slightly smaller than the last. Motors spinning at hundreds of RPM pull the wire forward, while reducing its diameter with astonishing precision. The process creates miles of wire every hour. The machine produces a constant metallic singing sound that echoes through production hall. Now comes one of the most important stages: galvanizing. The freshly formed steel passes through cleaning tanks that remove oils and oxidation. Then the material enters molten zinc maintained at approximately 450 degrees Celsius, or 842 degrees Fahrenheit. As steel emerges from the bath, a protective zinc coating forms across the surface. This thin layer becomes a fence's shield against corrosion, extending its life for decades. For vinyl-coated fencing, another layer follows. Automated extrusion systems heat polymer materials to approximately 180 degrees Celsius to 220 degrees Celsius, or 356 degrees Fahrenheit to 428 degrees Fahrenheit. The molten coating wraps around galvanized wire, while cooling systems immediately stabilize the surface. Bright green, black, or brown finishes appear almost instantly. What started as bare steel now gains additional weather protection and visual appeal. Meanwhile, chain-link weaving machines begin their remarkable work. Interlocking wire strands twist together in a synchronized dance of gears and motors. Some machines produce several feet of fencing every minute without stopping. Watching the process feels hypnotic. Wire enters from one side, and a finished diamond pattern fence emerges from the other. For welded wire fencing, robotic welding stations take over. Steel rods feed into positioning systems where electrodes apply precisely controlled electrical current. Temperatures at the weld point briefly exceed several thousand degrees Celsius. Tiny bursts of sparks flash across the line hundreds of times each minute. The result is a rigid mesh structure strong enough for farms, industrial facilities, and security installations. Wooden fence production follows a completely different path. Freshly cut boards enter giant drying kilns where temperatures often range between 60 degrees Celsius and 90 degrees Celsius, or 140 degrees Fahrenheit to 194 degrees Fahrenheit. Fans circulate heated air for days, sometimes weeks, reducing moisture content to control levels. The scent of warm cedar fills the building. Without this step, boards could warp, crack, or shrink after installation. Once dried, computer-controlled saws trim each board to exact dimensions. High-speed cutters shape decorative profiles, while sanding systems smooth every surface. Laser measurement systems inspect dimensions in fractions of a millimeter. Sawdust drifts through beams of light. Every board moves through the line with remarkable speed and consistency. Assembly comes next. Automated fixtures position rails, posts, and panels while workers oversee alignment. Pneumatic systems operating between 80 and 120 psi secure components with precision. Some factories produce hundreds of fence panels every hour. The rhythm becomes almost musical as machines clamp, fasten, release, and repeat thousands of times per day. Finished components then move through coating and finishing systems. Powder coating lines spray electrically charged particles onto steel surfaces before curing them inside ovens reaching approximately 200 degrees Celsius or 392 degrees Fahrenheit. As the coating melts and bonds, the surface becomes smooth, durable, and highly resistant to weather. The transformation feels almost magical. Raw industrial steel suddenly looks ready for homes, parks, and public spaces. Finally, giant packaging systems stack completed panels, rolls, posts, and accessories for shipment. Forklifts weave through warehouse aisles while scanners track every product. Thousands of feet of fencing leave the factory each day bound for construction sites around the world. Yet before a single shipment receives approval, one final challenge remains. The fences must survive a series of tests designed to expose even the smallest flaw. And some of those tests are far more brutal than you might imagine. Before any fence leaves the factory, an entire world of technology steps in to verify that every piece can survive years of punishment. Most people imagine fence manufacturing as simple metalworking, but modern plants often resemble advanced technology centers. Cameras watch every movement. Sensors monitor thousands of measurements each second, and artificial intelligence searches for defects invisible to the human eye. What happens here determines whether a fence lasts 5 years or 50. The first line of defense comes from laser measurement systems. As fence panels move down the conveyor, high-speed lasers scan dimensions at incredible speed. Some systems measure tolerances as small as plus or minus 0.5 millimeters. If a wire sits slightly out of position or a panel drifts beyond specification, computers flag the defect instantly. The process happens so fast that a human observer would never notice the problem. Then come machine vision cameras, mounted above production lines. These systems capture hundreds of images every minute. Advanced software compares each product against a perfect digital model. Tiny scratches, incomplete welds, coating defects, and alignment errors trigger automatic alerts. Imagine a quality inspector who never blinks, never gets tired, and never misses a shift. For galvanized fencing, coating thickness becomes a critical measurement. Sensors verify that zinc layers meet strict standards, often ranging between 45 and 100 microns depending on the product. That sounds incredibly thin, yet this microscopic shield can determine whether a fence survives decades of rain and humidity. Most people never realize that a coating thinner than a sheet of paper can protect steel for generations. Welded fence panels face another challenge. Every weld must withstand significant force without cracking or separating. Automated testing rigs grip sample sections, and pull with thousands of pounds of pressure. Steel groans under the load. Hydraulic systems hiss. Engineers carefully monitor the results because a single weak weld could compromise an entire security perimeter. But corrosion remains one of the greatest threats to outdoor fencing. That's why manufacturers perform accelerated salt spray testing. Sample panels enter chambers filled with a fine salt mist for hundreds or even thousands of hours. The goal is simple: simulate years of exposure in a fraction of the time. What looks like an ordinary steel panel suddenly faces conditions harsher than many coastal environments. Impact testing pushes durability even further. Heavy weights slam into fence sections to evaluate structural integrity. Security fences designed for industrial facilities often undergo especially demanding evaluations. The crash echoes through the laboratory. Metal vibrates. Sensors record every movement. Engineers analyze whether the fence bends, cracks, or returns to shape. Wood fencing faces its own series of examinations. Moisture meters verify proper drying levels before assembly. Technicians inspect knots, grain patterns, and structural consistency. Specialized laboratories expose samples to moisture, sunlight, and temperature cycles designed to replicate years of outdoor weathering. What happens next can reveal weaknesses long before customers ever see the product. Surprisingly, not every decision belongs to machines. Experienced inspectors still perform visual evaluations that technology sometimes struggles to replicate. A veteran quality specialist can spot subtle texture changes, unusual weld appearances, or coating inconsistencies that algorithms occasionally overlook. After years in the industry, many develop an instinct that machines cannot fully duplicate. This is one moment where human skill still beats automation. Factories also track rejection rates with remarkable precision. In top-tier facilities, defect rates often remain below 1%. Every rejected panel gets analyzed to identify root causes. Engineers study patterns, adjust equipment, and improve processes continuously. The goal isn't simply producing more fences. The goal is producing fences that perform flawlessly year after year. International certifications add another layer of confidence. Many manufacturers follow standards such as ASTM, ISO 9001, and EN quality requirements. Auditors inspect production methods, testing procedures, documentation systems, and traceability records. Every batch receives identification codes allowing manufacturers to trace products back through the entire production process. Imagine tracking a fence panel all the way back to the steel coil that created it. And this is where the story becomes even bigger than the factory itself. The fence industry now connects mines, forests, laboratories, robotics companies, shipping networks, construction crews, and millions of customers across the planet. Every panel that passes inspection joins a global system worth tens of billions of dollars. But just how large is that system? The numbers behind the world's fences are far more astonishing than most people could ever imagine. By the time a finished fence reaches its destination, it has already participated in one of the largest manufacturing networks on Earth. The global fencing industry generates well over $30 billion annually, with demand continuing to rise as cities expand, infrastructure grows, and security requirements become more sophisticated. Think about this. Every new neighborhood, airport, solar farm, warehouse, sports complex, and industrial facility needs some form of fencing. What seems like a simple product has become an essential part of modern civilization. Each year, manufacturers produce millions of tons of fencing materials and hundreds of millions of individual fence panels, posts, rails, and wire products. If all the chain-link fencing manufactured worldwide in a single year were connected end-to-end, it would stretch around the planet many times over. Most people see only a few dozen feet of fencing in their daily lives. The true scale remains almost invisible. China leads global production, accounting for roughly one-third of the world's fencing-related manufacturing output. The United States remains one of the largest consumers and producers of specialized fencing systems. India continues expanding rapidly through infrastructure growth and urban development. Germany contributes advanced engineering and premium industrial fencing products, while Brazil plays a major role through both raw material production and finished manufacturing. Together, these countries shape a significant portion of the global market. Behind these numbers stand millions of workers. Miners extract raw materials. Loggers manage forests. Steel workers operate furnaces. Engineers design machinery. Technicians maintain robots. Drivers transport finished products across highways and oceans. A single fence panel may pass through dozens of hands and countless machines before reaching its final destination. Most people never think about the enormous human effort hidden behind something so familiar. The history of fencing stretches back thousands of years. Ancient civilizations used stone walls, wooden barriers, and thorn-covered boundaries to protect crops and settlements. During the Industrial Revolution, mass-produced iron fencing transformed urban landscapes. Then came steel, galvanizing technology, automated wire weaving, and advanced corrosion protection. What once required weeks of manual labor can now emerge from a factory in minutes. Over the past 50 years, fence manufacturing has changed dramatically. Manual production lines gave way to robotics. Paper blueprints became digital models. Quality checks that once relied entirely on human observation now use lasers, sensors, and artificial intelligence. Modern factories can produce more fencing in a single day than some facilities managed in an entire month decades ago. And the future may be even more remarkable. Smart fencing systems already integrate cameras, motion sensors, intrusion detection, and network connectivity. Some security fences can automatically alert operators when someone attempts to climb or cut through them. Researchers continue developing stronger coatings, recycled materials, and manufacturing methods designed to reduce environmental impact while improving durability. Did you know that some high-security fencing systems are specifically engineered to delay intruders long enough for emergency response teams to arrive? Did you know that modern galvanized coatings can protect steel for several decades in many environments? And did you know that certain industrial fencing installations extend for hundreds of miles around massive infrastructure projects? Suddenly, a fence doesn't seem quite so ordinary anymore. Here's another surprising fact. Some of the strongest fencing products undergo testing powerful enough to simulate hurricane-force winds, vehicle impacts, and years of environmental exposure. Engineers intentionally push products to failure so they can understand exactly where the limits exist. Every broken sample helps create stronger fences for the future. And perhaps the most astonishing fact of all is this. Whether it's a small garden fence, a ranch boundary stretching across open countryside, or a security barrier protecting critical infrastructure, the manufacturing principles remain remarkably similar. Raw materials become engineered products through heat, force, chemistry, precision, and human ingenuity. The scale changes. The science remains. We began this journey with a simple question. How is a fence made? The answer took us from iron ore mines and managed forests to steel mills glowing hotter than lava. We followed raw materials across oceans, watched robots and workers shape them into finished products, and witnessed testing systems designed to catch defects smaller than the eye can see. What seemed ordinary revealed an extraordinary story hidden in plain sight. The next time you walk past a fence, you'll know something most people never do. You'll see the mines, the forests, the furnaces, the engineers, the laboratories, and the thousands of decisions hidden inside every panel and post. You'll understand that even the simplest products often represent some of humanity's most impressive achievements. And perhaps you'll start looking at the manufactured world around you a little differently. The next time you hold one of these in your hands, remember, it didn't just appear. It was born from the earth, shaped by fire, perfected by technology, and approved by the strictest standards in the world. That's not just a product. That's a masterpiece of human engineering. If you want to go deeper into the hidden world of manufacturing, tell us in the comments what product you'd like to explore next. Like this video, subscribe to the channel, and we'll see you inside the next factory.